So this is Discrete Maths, MATH1081, and we're having a look at a sample or selection of questions from Chapter 4, which is basically concerned with combinatorial mathematics. This question 37 is a particularly nice one on recurrences. And so we're going to analyse a particular problem, we're going to construct a nice recurrence, and then we're going to solve the recurrence and find a general formula that solves the original problem. So the problem is this: we start off with a 2 by n rectangle, and we've got some tiling squares. So I have a 2 by 2 square and I have a 2 by 1 square. And so I'm going to put these in here in some way, and I'm going to tile the 2 by n board. And so we let an be the number of ways of tiling this 2 by n block. Our aim then is to get a nice recurrence for this an, solve it, and then get a general formula for the number of ways to do the tiling. Well, let's just start off with a1, work out what a1's going to be. Well, if n is 1, then the block just is a single block like that, and there's only one way of tiling it. You take this one and you plonk it on there, and that's it, so there's only one way to do the tiling. For A2, if I've got a 2 by 2 block, well, then there are various ways of tiling it. I could just take one of these and plonk it on there, and there it is. Or I could take two of these ones here and put one there, and then I've tiled a 2 by 2 block. Or, remember, I could turn it around, and so I could tile the block like this and put the tiles that way, and that gives me a third tiling. So there are going to be, in fact, 3 ways of doing A2. For A3, normally I'd stop there, but it might be good to just to check A3 to make sure we double check everything. For A3, well, what are the different ways of doing it? We could have a 2 by 2 block followed by one of those, or we could have it the other way round and put the 1 block there and the 2 block there. There are 2 ways of doing it. I could simply have 3 of these single blocks. That will be another way of doing it. On the other hand, I could, in this picture here, I could replace this 2 by 2 block with 2 going that way, or I could do the same in the other one. So I would do there plus there. And so in fact there are 5 different ways of tiling the block if I've got a 2 by 3 block. Well, now you see after this it's just too complicated to try and do it by hand. You'd go crazy trying to work out the number of them, and you may miss one or something. I certainly would. So at this point I want to try and construct a recurrence. And the idea of a recurrence is you want to relate an to an, but for smaller values of n. For smaller values of n. Now there are different ways of thinking about this. I like to think of this as follows. I imagine that I've done all the tiling. I've tiled the whole 2 by n block and I finished, and I stand back and look at my handiwork and I look at it and ask the question, well, how did I finish? What was the last thing I did? How did I finish? What was the last thing I did? So I can end the block by doing the following. So here's my 2 by n block. So I've got something happens in here. I could have finished it by simply taking one of these little 2 by 1 blocks and plonking it on the end, and there it is. There's my 1 by 2 block, and I finished. That's how I ended the tiling. Now in that case, this up to here would now be n minus 1. Up to there. So the number of ways of tiling it up to there would be a sub n minus 1. There's that many ways of tiling it up to there. And finally, I plonk one of those on the end. So often in these discrete maths problems, it often gives you the answer, which I think it may do here, and asks you to explain it. It gives you the answer and asks you to explain it. So you can't just write it down because it's not explaining terribly clearly. So one way I like to set this out is just to put a little arrow here. I've drawn my picture, And so this one here, I simply add a 2 by 1 block, and I've got a picture there to show what's happening, and that's probably enough. So I add a 2 by 1 block. Perhaps you should say 2 and 2 by n minus 1 block. Perhaps I should say tile, there might be a bit less ambiguous. So add a 2 by 1 tile to a 2 by n minus 1 block. Well, that's not the only way I could finish the problem. I could finish doing the tiling. Alternatively, I might have put one of these big 2 by 2 blocks on the end. So I might have put a 2 by 2 block on the end. And then this would now be an n minus 2 block. So I could have done that, and while I'm doing this, I could also have done this. I might have put 2 of these ones, but sideways. So I might have finished it off like that and put a block tile there and a tile there, and once again this will be an this will be of length n minus 2, and that's the only other way I can finish it. Now if that was the case, then I will tile up to n minus 2, and there's that many ways of tiling up to that point, and then I put either one of those or one of those, so I get 2 of those. And so explanation here, we add either a 2 by 2 tile or 2 1 by 2 tiles. And again, I've drawn the picture here so it shows what's going on. So there's the recurrence that we wanted. It tells us how to relate one of the tilings back to earlier tilings when you've got n minus 1 or n minus 2. We can just quickly check that that looks right, because according to what we saw here, this number should be that number plus twice that one. And it is. You get 3 plus 2 times 1 is 2. Gives me the 5. So that's looking good. It tells me that it looks pretty correct. Also, of course, in the question they gave you the recurrence and ask you to show it. And so I should just say here 4n bigger or equal to 2, this is true. Okay, so the next thing now is we'd like to get a nice formula. This gives me the recurrence, but it's only a simple second order recurrence. So I'd like to get a nice formula for solving this recurrence. So I'll just copy these numbers here so we can check them a bit later. So A1 is 1, A2 is 3, A3 is 5. So I'll just copy those there. And now I'm going to solve the recurrence and see what we get as a nice formula for this. Now this in fact is a very easy recurrence. It's a second order homogeneous recurrence relation with constant coefficients. There's no forcing terms. It's all nice and simple. So my next step is I'm going to solve an minus 1 minus 2 an minus 2 is 0, subject to these initial conditions. So I write down the characteristic equation. This is now a standard problem that you've learned how to solve. So I get lambda squared minus lambda minus 2 is 0. I factor this quadratic, so I get 2 and 1. I'll get minus plus. So lambda is going to be 2 and minus 1. So we just solve the quadratic. So we can write down our general solution. So the general solution is going to be, an is going to be a linear combination of powers of 2 and powers of minus 1. It's a times 2 to the n plus minus 1 times b to the n, and we don't know what these coefficients are, a and b here, but we can use the initial conditions to calculate these. Now I can just substitute in A1 and A2 into here. Let me just perhaps show you a little trick at this point, which I often find useful. Doesn't make much difference here because the numbers are so simple, but sometimes if these are complicated quadratic surds here, then substituting in 1 and 2 can be quite complicated. So let me show you a little trick here. The recurrence says that this number is that plus twice that. So working backwards, even though it doesn't make physical sense to have a board with n to be 0, you can't do much tiling on it, but at least algebraically we can work out what A0 ought to be in order to satisfy the recurrence. So again, that is this plus twice that. This one is this plus twice this. So A0 will have to be 1 in order for the recurrence to work, that this number is that plus twice that one. You can also think of it like this. There's one way of tiling nothing. You just don't do anything. Anyway, that's one way of thinking about it. But doing it purely algebraically, we get that. And so I can now substitute those in, and it makes the calculations a little bit easier. So with A0 is 1, tells me that 1 is equal to A plus B, and A1 is 1, tells me 1 is equal to 2A minus B, and I can solve those simultaneous equations. Obviously, if I add them, I'll get A will be 2/3, and then A plus B has to be 1, so that's going to be 1/3. So there's the solution to the recurrence. Let me just put this together now and show you the formula. That we end up with. So, and I can simplify it a little bit. So AN then, putting back the 2/3, notice I've got a common factor of 1/3, so I may take that out, and I get 2, so I put a 2 in here, I can bump that up by 1, so 2 to the n plus 1, and then I get a 1/3, so I get plus minus 1 to the n there, taking out the third. And so there's the nice closed formula solution, and again, we should check it works. This is always a nice thing in maths. You can check things make sense, check they work. So according to this, when I put 3 in, I should get 5. So A3 should be 1/3, 2 to the 4th, plus minus 1 cubed. And 2 to the 4th is 16, minus 1 cubed is minus 1. 16 minus 1 is 15, divided by 3 is indeed 5, and so that's looking good. And so there is the solution to the problem. It's a nice problem because you would not be able to guess intuitively that the number of ways of tiling this rectangle using these two comes out to be something as intricate as this formula here, and yet this gives me the right formula. So for example, if you wanted to know how many ways are there of doing it, if you've got 7, a 2 by 7, you just plug it in, you get 1/3 times 2 to the 8th plus minus 1 to the 7. So the 2 to the 4th is 16 squared, it's 256. Minus 1 is 255 divided by 3, and that gives me, it gives me 8. 85. So in fact, you wouldn't want to do it by hand, so there are in fact 85 ways of tiling this if I go along 7 centimetres along the bottom. But you can get it out nicely from the mathematics. Of course, you wouldn't want to do it in practice by hand.